Okay, welcome to GADEPs seminar. So today we have Jeanine van Order going to talk about automorphic green functions and I forgot.
I did too. On Shimura varieties and Kummer periods, but periods, maybe
okay, exactly.
Skip the word
Kummer
because we're not going to talk too much about that's the very, very last bit. Okay, first of all, thank you so much for the invitation. It's an honor to speak here. Advanced apologies, the talk will be largely expository and there will be some overlap with the talk I gave last term. So here, the title is automorphic, and please shout out if you can't read my writing. I have a habit of automorphic Green's functions and periods. So we just had a brief discussion about this before the lecture, about the conjecture of Birch-Swinnerton-Dyer and periods. And so without going into a full explanation of what the conjecture states, let me just remind you that on some level, the conjecture predicts that the central derivative value or higher derivative value of the Hasse-Weil function of an elliptic curve defined over a number field, assumed to have analytic continuation to an entire function with a functional equation, etc., that higher central derivative value should be related to a non-zero algebraic number times the regulator of the elliptic curve. So let me just say that very briefly so that we can focus on this aspect of it. So we expect, so if you have E is an elliptic curve, and you have that is defined over a number field, typically we take the number field to be Q or an imaginary quadratic field in the rest of this discussion. And we write, okay, so we consider its group of k rational points has the structure of a finitely generated abelian group, thanks to theorems of Mordell and Weil. And we know that, okay, so we consider the Hasse-Weil function, which we know in some cases, conjectural in all cases, to have an analytic continuation to an entire function, satisfying a functional equation of the form relating values at s to 2 minus s. And conjecture of Birch-Swinnerton-Dyer predicts, among other things, that the order of vanishing at the central point is equal to the rank of the group of k rational points, but actually that the leading term in the Taylor series expansion. Yeah, okay. Let me just write this out. So we know this in some cases. Has an analytic continuation. Can I write on both? I can write up until that point? Yeah. Analytic, to an entire function. Let me call that lambda, which satisfies a functional equation, etc., but with order of vanishing at the central point, which take to be 1/2 in the classical normalization, is equal to the rank, and actually that the leading term in the Taylor series expansion around s equals 1. So minus REK of this So basically this should be given, so the leading term in the Taylor series expansion around s equals 1 of this completed L function should be given by some rational number, which is given in terms of It's a very precise product of the cardinality of the Tate-Schaff-Ravitch group, which we expect to be finite, the product of all the local Tamagawa numbers, the periods divided out by the cardinality of the torsion subgroup squared, times the regulator. Okay, and so this is the prediction. So for kappa, some precise non-zero rational number, which I won't describe here, but we have a very explicit formula for it, and REK, the regulator. So the regulator, the way it's defined, is you fix a basis. You fix a basis E1 for the group modulo the torsion points, and you evaluate you consider the matrix, first of all, given in terms of the Néron-Tate height pairings of the various basis elements, and you take the determinant. And so that's somehow intrinsically how we expect to be able to characterize the central derivative value of, So this should be the Rth central derivative value should take this form. And what's more important here than the rational number is the regulator. Now, there are, before I go on, we expect more generally, where's the eraser? So we still don't know how to prove Birch-Swinnerton-Dyer conjecture when the rank is 2 or greater. But what we expect, more generally, according to the philosophy of Kontsievich and Zagier, is that so we expect, more generally.
You can use also all these boxes.
Oh, yeah, thanks. That's helpful because I'm going to be erasing prolifically. Yeah, let me say in a nutshell, first of all, what I plan to write. We expect more generally that the central derivative values of the Hasse-Weil function will be periods in the sense of Kontsievich-Zagier, which is to say complex numbers whose real and imaginary parts can be expressed as integrals of rational functions with rational coefficients over domains determined by polynomial inequalities with rational coefficients. So I'll write that in a minute. And the philosophy here is, if you assume the Tate-Schaff-Ravitch conjecture, just ignore that, what you would expect, what you can show, using calculations due to Spencer Bloch, given in a paper of Gross and Zagier, is you can show that the regulator is a period. And in fact, you can show, if you assume the Tate-Schaff-Ravitch group is finite, that this is a period. So in general, we expect that these central derivative values are periods, and then, again, ignoring the cardinality of the Tate-Schaff-Ravitch group, we expect that in a finite number of steps, if you could establish that, if you know that one side is a period, and you know the other side is a period, you expect that in a finite number of steps, you can show an equality to prove Birch-Swinnerton-Dyer modulo the Tate-Schaff-Ravitch conjecture. So we expect more generally that, that the Rth central derivative value so S equals 1 is the central point, is a period. So period in the sense of Kontsievich-Zagier, so a complex number whose real and imaginary parts can be expressed as integrals of rational functions with rational coefficients so over integrals or domains given by a polynomial inequalities with rational coefficients. So Examples include, okay, so examples include algebraic numbers. So let me just, in parentheses, write a couple of examples for you. These, really, they should be like a subset in between the algebraic and the transcendental numbers. They should be numbers that you can construct. So examples include algebraic numbers. So for instance, you have something like the square root of 2. Can be expressed as an integral over 2x squared less than equal to 1 of dx. A number like pi, which is 3.14, etc. It's not an algebraic number, but it can be expressed as an integral of the form, double integral of the form x squared plus y squared less than equal to 1 dx dy. Also, logarithms of algebraic numbers turn out to be periods. This is all a parenthetical remark, so something like log 2, logarithm of an integer, has such a presentation. You can write it as an integral from 1 to 2 of dx over x. So I'm not going to dwell on this, but these periods are numbers that you can construct, and there's supposed to be some set that contains the algebraic numbers, but not all of the transcendental numbers. So for instance, we do not know whether or not E is a period. We do not know whether or not the Euler-Mascheroni constant is a period. We suspect they're not, but we don't know how to prove it. But what we expect is that these numbers that we want to study in arithmetic geometry, the central derivative values of these Hasse-Weil functions, ought to be periods. And remarkably, we know how to do that in general when the rank is 1. In a very special case, at least. And I want to explain that picture, first of all, how it arises in the theorem of Gross and Zagier. But then more generally, there's a more modern way to approach proving such a formula, at least in a rudimentary case, in terms of automorphic Green's functions. And then we have a sort of broad conjecture that the automorphic Green's functions themselves take values in the periods, in the ring of periods. And actually, you can deduce a lot towards that from what's computed in the literature, as I would like to explain. But then there ought to be a sort of K-theoretic interpretation of that. So I'd like to sketch the panorama. I will have to go quickly in the interest of time, but I'm happy to answer questions afterwards. So we have a special case where we can, special case where this works. Is roughly, I'm simplifying a little bit, is if you have, for K an imaginary quadratic field, you can descend down the Q, but it becomes a little bit sophisticated. You have to talk a lot about like Waltz-Bourget and different theorems. So let me just work over an imaginary quadratic field. And for E, okay, so actually, I'll assume throughout that the elliptic curve that we start with is defined over Q, so that it's modular by work of Wiles, Taylor-Wiles, and Breuer-Conrad Diamond-Taylor, so that we can take for granted the properties of the L function that I wrote down before. And so in this case, if we assume that E is an elliptic curve defined over Q, then by modularity there exists a capital eigenform of weight 2, a level equal to the conductor of the elliptic curve, such that the Hasse-Weil function of the elliptic curve over Q is none other than the Mellin transform. Maybe just shift by half to use the automorphic normalization. And in this situation, if we base change to K and consider any Hecke character of K, then what happens is that the Hasse-Weil function of E over K, twisted by any Hecke character. Of course, we're only going to look at the trivial class group character and what follows, but for any Hecke character chi of K, actually the corresponding Hasse-Weil function over K twisted by Hecke character will have an analytic continuation given by the Rankin-Selberg function of F times the theta series, the Hecke theta series associated to the character. So
the rank of E over Q itself can be 0 and 1, over K is 1.
Over K, 1. Over 1. precisely. It cannot be, yes, that's right. That's right. Yep. And so the cases that will be interesting are the cases where both the rank over k and the rank over, well, there are two cases to consider, right? Like the rank over k is 1. The L function actually decomposes. If you take the trivial character, this L function decomposes into a product of the L function of f times the L function of the quadratic twist. And then what that means is that one of those guys has to have a 0 at the central point. And so you have two options. But yeah, I want to assume, well, okay. It's not going to be immediate in what I write, but looking at a situation where the rank over k will be 1. Let me explain that very quickly. What happens here? So yeah, maybe I should write this. So these are going to be completed L functions. The Euler product will be over all of the primes, and these are entire functions. Even if you take the character to be trivial, these are entire functions. And what we know in this setting is that the functional via the connection to the Rankin-Selberg L function, the Hasse-Weil function will have completed Hasse-Weil function. Let me just take the trivial character. Will have a functional equation of this form. So we have the functional equation where so this eta is simply the quadratic Dirichlet character. So the quadratic Dirichlet character associated to the imaginary quadratic field. And this is an odd character. And the point of writing this down is that if we assume the following things, so if we assume that assume for simplicity that the level or the conductor is square free, and co-primed the discriminants of the imaginary quadratic field. What that means is you can decompose n into a product of a square free product of primes which split in k times the square free product of primes that remain inert in k. So v divides n plus if and only if v splits in k, and v divides the inert level if and only if v is inert. So the point is, we can characterize the situation where the root number is -1, right? So if we assume that the level is square free, given by a product of an even number of primes, then because of the fact that the Dirichlet character will be odd, this will be -1. This will be equal to -1. And what that means is that the central value at s equals 1 has to vanish. And that's exactly the situation where we expect to have rank 1 or odd rank. So the theorem of Gross and Zagier phrases that condition as the Heegner hypothesis. It's equivalent to having Heegner points on the corresponding modular curve. Yep.
It's a kind of state. If the f function of the elliptic over q, this modular form, f
yes.
over k, you will have some character k.
No. For any Hecke character. So for any Hecke character, including for the including the trivial character, right? So you have something more general. This is a consequence of modularity. This is a lesser known consequence, which is implicit in Gross and Zagier's paper, that if you know that the elliptic curve is modular, and hence that its L function is given by this, what you can deduce, it's more or less a lemma, is that the analytic continuation of the Hasse-Weil function of E base change to K, twisted by, you could remove the character here, but I'm just saying more generally, for chi any character, you know that that Hasse-Weil function will have an analytic continuation given by shift of the Rankin-Selberg L function of the eigenform parameterizing E times the corresponding Hecke theta series. Yep. So this will be a degree 4 L function over Q. But if you base change, it's via the theory of cyclic base change, this is also equivalent to, like you could also take the, let's say you have the GL2 automorphic representation corresponding to, Yeah, so there are three ways to present this. I mean, there's a different way to present the cell function too. So this, you can consider the base change of the GL2 representation twisted by the character. This is degree 2 over k as an L function over the imaginary quadratic field, but has degree 4 over q using a theorem of Ramakrishnan. Anyhow, yeah, it's a slightly more general statement. We only want to look at the trivial character here, like trivial class group character, but more generally, you can deduce this from modularity. And this deduction is implicit in the paper of Gross and Zagier. They don't explain it, but they do, in fact, derive it in the course of their calculations. So I want to state what Gross-Zagier proved in terms of what I wrote before. What it does is it verifies precisely what I mentioned before. It shows that the central derivative value, in the setting where the Heegner hypothesis is satisfied, I'll write this down, that the central derivative value of the L function is given by a non-zero rational number times the regulator. And the regulator will be actually the Néron-Tate height of the single generator. There will just be one basis element. And it will actually be some sort of linear combination of Heegner points on the modular curve. Now, I'll state that very quickly because there's a different proof of it, which is in a broader landscape of spin-Shimura varieties. And there's a really neat idea where you can realize those values essentially as the evaluation of automorphic Green's functions along 0 cycles on the Shimura variety. And after making this connection, it becomes immediate. I mean, after subsequent calculation, either I will explain that you have one of two cases to consider. One situation where the input form is weakly holomorphic. You can deduce from the theorem of Borchards that the values are periods. They will be logarithms of algebraic numbers. But in the more general setting, where you don't have that, you have these other calculations due to Brunier, Young, Andriata, Gorin, Howard, Matapusi-Pera, which allow you to realize the evaluation of those Green's functions along CM cycles as Falting's heights or arithmetic heights of CM divisors along 0 cycles of a Shimura variety, from which it's also sort of apparent that the values have to be periods. And so this isn't written down in the literature, but it's all somehow there if you think about it. And we expect that there ought to be a nice sort of abstract interpretation of that. But let me first remind you of the Gross-Zagier formula, which more or less verifies the first assertion of Birch-Swinnerton-Dyer. I'm being a little bit simplistic about the rational number, which is a delicate matter. That's a different story, but still, we can express things this way. So theorem of Gross-Zagier, 1986, is with the setup above. So E is an elliptic curve defined over Q, parametrized by some modular form as above. I won't repeat the whole setup. So K is an imaginary quadratic field of discriminants prime to the level. The level is assumed to be square free and to have this decomposition. If we assume that the square free level has a NERT part, where that is with respect to the decomposition, is a product of an even number of primes, so that the root number vanishes. So that the root number is -1 and hence the central value vanishes. Then we have the following formula. So really the theorem is given in terms of the Rankin-Selberg L function, but let me state it here in this simple form. So you have the central derivative value of the Hasse L function of U over K. They prove a more general statement, but I just give it here in this special case. Will be given by 8 pi squared times the Peterson inner product of the eigenform times the class number of K times the number times half the number of roots of unity in the field squared times the Néron-Tate height. Let me write this carefully. So Néron-Tate height of some Heegner divisor. Let me specify what everything is. So here, HK is the class number. So the class number, the UK is the 1/2 the cardinality of the group of roots of unity in K. So it's going to be a small number, which doesn't matter so much. This is the Peterson inner product, or product or norm of F with itself, or the norm, Peterson norm of F. And this here is, in this case, a simple linear combination of Heegner points of discriminant dk on the modular curve projected to the F isotypical component of the complexification of the Jacobian. So let me just write that quickly. Yes, and so here the CF is given as follows. So you have some sort of sum over classes in the class group of K of some. Okay, so we're not twisting by any character here. We're just taking it to be the trivial character, and then we have, so C. Let me just call it C1 because we're twisting by the trivial character, and then C1F, which we also write as CF, is the projection to the F isotypical component, typical component of, so the modular curve on which F is a function will have a Jacobian, and we look at its complexification, and there will be an F isotypical component determined by the action of Hecke operators. And so this, so in a nutshell, this formula, through the connection to the Néron-Tate height of what turns out to be a generator for the Mordell-Weil group modular the torsion, will give us.
I imagine the same formula for E over Q must be a little bit simpler.
It's a little bit delicate. So you need to consider, as I mentioned before, so there's a separate paper by Gross, Koenen, and Zagier which spells it out. You have to be careful because you have two factors, and you want to specify which factor. There is a formula that can be deduced, but it's delicate, and it's also phrased remarkably in terms of the Fourier coefficients at D of the Shimura lifts of the eigenform. It's actually a little bit more, surprisingly, it's a little bit more delicate because you have to consider these factorizations of the L function, and so you have to sort of specify where the point is coming from. The formula itself is simpler, but the deduction of it is somehow not. The main calculation of Gross and Zagier is for one of these base changed to K L functions. This Rankin-Selberg L function has a lot of structure which can be utilized, essentially coming from the theta functions. And descending to Q is actually pretty delicate. The formula ends up being more or less the same, at least up to the class number. but nevertheless, it's delicate to work it out. The second paper by Gross, Koenen, and Zagier spells it out in a more understandable way than Gross and Zagier do. So what Gross and Zagier explain is that in their paper, at least with the right conditions, you end up with, okay, so actually if you consider this in terms of the decomposition, so yeah, there will be natural decomposition of this L function, and the L function you look at curve E over Q times its quadratic twist by K, and one of those factors will vanish at the central points, and so yes, you can deduce that for one of the factors, the corresponding Taylor series expansion around S equals 1 will have the predicted form, and for the other one, there will also be the predicted form, but it's delicate. You have to do a little bit more work. So here, I mean, what we get for free is that this assertion can be verified for the case where the rank is 1. There's going to be a way to identify this. I'm being a bit vague with the regulator. Right? The regulator will, in fact, it'll be the determinant of a 1-by-1 matrix. It'll simply be the Néron-Tate height of a generator, okay, which will be a Heegner point. So we don't know how to do this in general. We don't know how to do the analogous. We don't know how to make the analogous connection to the regulator when the rank is 2 or greater. Not even for a single example do we have an analytic theorem for the L functions. However, we do have this different proof of Gross and Zagier, which emerged in the past 10 years, or 15 years, due to Brunier and Yang, using ideas due to Borchards and these regularized theta lifts, which can be realized as automorphic Green's functions on some Spin-Shimura variety. So depending on how much time, do I have half an hour? Yeah. Good. Let me explain this. So there's a different way, there's a completely different way to prove Gross and Zagier, which sort of reveals more structure to the problem. And I would like to explain that in what time I have, and also why it is that the automorphic Green's functions, which somehow run the show, it's very tricky to see, in my opinion, that these are Green's functions. This is a theorem due to Brunier and Borchards. Yeah, it seems to be that these functions, when you evaluate them as CM points or along CM cycles, will be periods. And, well, it suggests that the approach of Kontsievich and Zagier might indeed be correct, although I don't claim anything for the higher rank cases. So let me explain a little bit more this modern viewpoint, which allows, you can realize the theorem of Gross and Zagier is a special case of a more general theorem, which emerged in the past 15 years. And so I'd like to say what it is without being too technical, although it is unfortunately necessarily a bit technical to state. So let me just, yeah, so a new viewpoint. So a new viewpoint. A new viewpoint which leads to lots of periods, okay. So is that there's a different way. Okay, so combining, what I'm talking about combines various works, in particular works of Borchards, Brunier, Brunier-Yang, and others. Okay, so I'm not, there are others as well. There is a new approach to proving the Gross-Zagier formula and higher rank analogs in the sense of higher rank group. Yeah, so not higher rank has two senses here. It's a higher rank group, but not higher Mort L rank. No. At least not a priori. So here, the more general setup will be the Spin-Shimura variety, and these will be parameterized by. So let's just fix a rational quadratic space of signature N2. So rational quadratic space of signature N2, where N is a positive integer. So for instance, like trivial example of a CM cycle will actually be the case where you take the quadratic field to be an imaginary quadratic field, and then you take the quadratic form to be -1 times the norm homomorphism, and that will determine a rational quadratic space of signature 0, 2. We can also consider, to recover the case of modular curves, we could consider the rational quadratic space where V is given by the Q vector. It's just rational means over Q. So like if you take V to be the 2 by 2 matrices with entries in Q but trace 0, and you take the quadratic form to be -1 times n times the determinant of a matrix, that will give a rational quadratic space of signature 3. Okay, so we have a rational quadratic space of signature N2. We consider the Grassmannian of oriented 2 planes, or like subspaces of dimension 2 of VR, for which the restriction of the quadratic form is either totally is positive or negative. You have some choice in that. And then you consider, we consider the corresponding spin group. This will be an algebraic group defined over Q. We then have, you fix a full rank, fix a maximal lattice. So write LV to note the dual lattice, and this will, in fact, this will determine a compact open subgroup or a level structure. Let's call it U. This is a U on the finite adelic points of G. And with this information, what we get is a spin Shimura variety. Okay. Or maybe I should write this the other way. Spin Shimura variety with complex points given by the usual double coset. Okay, divided out by this compact open. This, I won't say it, but there's a way to decompose this. Okay, well, I mean, I just write it and put it in parentheses. You can actually view this as being a, you can fix a set of representatives, a finite set of representatives for this space, and then consider, I mean, these will be given by simpler objects. You have some sort of a connected component. You fix a connected component to the Grassmannian. These, you get some arithmetic subgroups determined by intersecting the rational points with the connected component of the identity of the real points with the G conjugate the compact open. Okay, so I'm not going to go into this, but you have this Shimura variety. It is defined over Q. It's quasi-projective of dimension n. It's smooth if and only if the compact open is neat or it has some condition. And these are well studied. These have many cycles on them. Roughly speaking, any rational quadratic subspace of signature n prime 2, where n prime is any integer between 0 and n minus 1, will give rise to a cycle. So these are very nice Shimura varieties to study. They have lots of cycles on them. So we recover the modular curve. So we recover XU to be the non-compactified modular curve if we take, as I said before, the rational quadratic space to be the 2 by 2 matrices with entries over Q. And the quadratic form is -1 times n times the determinant map. Okay. And so that will recover the modular curve. And so the theorems that I state for this more general setup will ultimately allow us to recover the Gross-Sagier formula by this very special case. So here, and so the level, I'm not telling you the level structure. There's going to be a recipe for the U. Like the U will be given very explicitly as decomposed into a product over all UP. Each UP will be a compact open subgroup of a GL2 ZP of the expected type, where the lower left coefficient is a congruency 0 mod n. I won't go into that. What we can do is reprove. We're not going to think about elliptic curves anymore. So really, if you look at the way Gross-Sagier is proved, nothing really is about elliptic curves except for the moduli description of the modular curve. So everything is a statement. So the geometry that appears in the proof of the Gross-Sagier formula is the geometry of the modular curve, i.e. the compactified modular curve x naught of n. And what they do is they consider moduli description, and like the CM points there can be parameterized as pairs of elliptic curves with complex multiplication by a given order in O of k. And that's how it appears. Here, it's not necessary to use a moduli description, but what you do instead of studying the modular curve is more generally you study the geometry of this spin-Shimura variety. And what happens there is it turns out to be a theorem that any zero cycle on this spin-Shimura variety will take the form that I described before. It'll come from a rational quadratic subspace of signature 0, 2, and that will always determine some imaginary quadratic field. And so that subspace of rational quadratic subspace of signature 0, 2, which is secretly an imaginary quadratic field, kind of embeds. It gives a zero cycle in the spin-Shimura variety, and those zero cycles are sort of geometric realization of CM points or Heegner points in general. And what happens, as I'll explain, is there is some sort of regularized theta lift. Borchard's found a very clever way to modify the classical construction of a theta lift to construct meromorphic sections inside some line bundle over the Shimura variety. I will explain this quickly if I can. I can go into a lot more detail if people like. And this function has remarkable properties. One is that if the input form used to describe it comes from a weakly holomorphic form, this regularized theta lift will give rise to a meromorphic function. I'll state this theorem, and you can say what the divisors are precisely. It's a pretty remarkable theorem of Borchard's, which was subsequently refined by Brunier. And so even in the settings where the input form doesn't have this special property, you have a way of thinking about these regularized theta lifts as automorphic Green's functions on these Shimura varieties. And once you have these Green's functions, you get arithmetic divisors. You know what the divisors are thanks to the theorem of Borchard's refined by Brunier. So you have these arithmetic divisors. So on the one hand, you have a calculation of Brunier and Yang, which allows you to evaluate these Green's functions, so these regularized theta lifts, along these zero cycles coming from imaginary quadratic fields, and to recover some sort of constant coefficient of some modular form minus the central derivative value of some Rankin-Selberg function, which in this special case will give you the Hesse-Weyl function of the elliptic curve. That's not obvious though, but that's what happens. And because it is an arithmetic height, because subsequent calculations allow you to identify that calculation as being the Archimedean component of an arithmetic height, or excuse me, the Archimedean component of an arithmetic height, or an automorphic Green's function evaluated along a CM cycle you deduce for free that is a period. Let me explain that in a bit more detail. Is everything clear? Okay. Here I have this, unfortunately, there are some modular forms, some vector-valued modular forms that sort of run the show, and I have to write them down. I won't write their Fourier series expansions, but the spaces of these forms seems to be, these forms themselves, their Fourier coefficients, and a certain exact sequence of these spaces of forms seem to really govern the arithmetic behavior. And we suspect there's going to be some K-theoretic analog of these spaces and these exact sequences, but we're still sort of working out what happens. So here, may I use this board? Okay, so Borchard's used some variation, a highly non-trivial variation of a theory of theta lifts to construct meromorphic sections in some line bundle, or some sort of tensor product, a line bundle over these Shimura varieties. So very roughly speaking, to give something concrete, if you start with, so maybe I just write this down here. So these will be given, these so-called regularized theta lifts, which turn out to be Green's functions, will be, let me establish some notation here. So write a generic point write a point in the C points of the Shimura variety as ZH. So Z is the Grassmannian variable, and H is an element of the finite adelic points of the G. And here if you have, if Fk is a harmonic weak mass form of weight K and Weil representation associated to the lattice, so weight K equals 1 minus n over 2, where n is the dimension of the positive part of the space, then this regularized theta lift is given by some sort of limit limit over truncated fundamental domains. So T is going to be a positive real variable. You have some truncated fundamental domains. You take the standard fundamental domain for the complex upper half plane, but then you insist that the real part is sort of constrained to be between -1/2 and 1/2, that tau times tau bar greater than or equal to 1, and that the imaginary part of tau is bounded by T. Okay, so this is just standard fundamental domain, but you want to truncate. I'll say what everything is. You have some sort of pairing on vector valued forms. So here you have harmonic weak mass form. You have some Siegel theta series associated to the lattice L. And then here so tau is U plus IV in this notation. And so here, let me just say what everything is. And by making this precise, I can go on to explain why we get periods. So here, so omega L is the okay. So this is so functions on the dual lattice mod the lattice. So this is the Weil representation associated to the lattice. This is a Siegel theta series. And F, as I wrote before, is a harmonic weak mass form of weight k equals 1 minus n over 2 and Weil representation, or representation omega L. So yeah, this, I should maybe say a little bit more about, these functions will decompose, so without saying too much about them, they'll decompose into like a holomorphic or principal part, and then into a rapidly decaying non-holomorphic part. And why they're called harmonic is because they happen to be Laplacian eigenvectors of eigenvalue 0. And so these, that property leads to having a decomposition into holomorphic part, which is really what plays the major role in the arithmetic. Without writing down the Fourier series expansions, I just say with Fourier coefficients of the positive part written in this way. So I'm just going to write FCK, like the plus part, and they're going to be indexed by cosets of the, okay. I'll write this down later. And so here, this is the input data. And here, in fact, there is an important exact sequence coming from an antilinear differential operator. So let me call it psi k. K is now 1 minus n over 2. And what this will do is go from the space of harmonic weak mass forms of weight k and representation omega L to the space of holomorphic vector valued cusp forms of weight 2 minus k and contragradient representation. And specifically this form, or this operator will act, it's a kind of level lowering operator. So it's going to be given explicitly as an operator of the form like 2. Now let me just erase this. It's some kind of level lowering operator, modification of a classical level lowering operator. And this gives rise to an exact sequence of spaces of vector valued mass forms, which is really important for the theory. So we have 2 IV. It's a tau equals U plus IV.
If k is a real function, that can't holomorphic.
Sorry?
If k is real.
So k is a number. K is a weight.
No, fk, this fk function.
Fk is a vector valued.
Okay.
It's a vector valued.
Holomorphic or real?
No, it's not necessarily holomorphic. I'm getting to that.
That's why
I'm getting to that. In general, no. In general, they're not holomorphic. And the ones that give you the central derivative values will not be holomorphic. The ones that give you the Borchard's products, giving you the logarithms of algebraic numbers will be weakly holomorphic. And so this is actually really key. Now here let me just write down what this operator is quickly. So to the k, 2iv to the power of k, delta fk complex conjugate over delta tau complex conjugate. So this is some sort of explicit level lowering operator, which gives rise to an important short exact sequence. Okay, so this is a very important short exact sequence of these spaces of forms. So let me just say verbally. So we end up having this space I call mk shriek omega L, which will be the kernel. So let me just write this down. You have the space of harmonic weak mass forms, which are not generally holomorphic. They're going to be vector-valued forms of weight k equals 1 minus n over 2, which happen to be Laplacian eigenvectors of eigenvalue 0. And then this anti-linear differential operator, which is really just some sort of level-lowering operator, will have image in the space of cuspidal vector-valued forms, holomorphic cuspidal vector-valued forms of weight 2 minus k for the contragradient representation. And this space here, which can be characterized as the kernel of this map, will be the weakly holomorphic forms. Okay, so it'll be the weakly holomorphic vector-valued forms of weight k and V representation L. And the distinction is really important. What happens if you take the regularized theta lift? So if you take the regularized theta lift of one of these forms, it really does matter whether or not you're in the kernel or not. If you're not in the kernel, you get a relation to the central derivative value of some Rankin-Selberg-L function. Okay, so let me write down what you get. If you're, and one more, okay. This exact sequence is key, and this is exactly the exact sequence we think there is a k-theoretic analog of, which gives us motivic cohomology classes, which will allow us to realize the regularized theta lifts or the automorphic Green's functions as certain pairings defined in motivic cohomology. But from the analytic point of view, we have the short exact sequence, and one more piece of notation that I give to be able to state is if we're given two vector valued forms. So I want to say what this double brackets, this thing is. If you're given two vector valued forms, so if you're given, let's just use the notation AK for like space of vector valued forms. It doesn't matter if they're cuspidal, holomorphic, just vector valued forms of weight k and representation omega L, and you're given some other form G, let's call it, also in this space, but with the contragradient representation, then what this notation means, I'm going to be kind of brief about it because I don't want to write out the Fourier series expansions, but the Fourier series expansions of the vector valued forms, they're kind of like double expansions. So there's going to be one sum over cosets mu in the dual lattice modulo the lattice. And then for each of those cosets, there's going to be a scalar valued modular form with a standard Fourier series expansion. And so here, this pairing will sort of reflect that. And what it'll be is the corresponding sum over cosets of the dual lattice mod the lattice of the corresponding linear combination. So this is going to be for this coset, so like, for instance, the FT will have an expansion of this form. It'll be like the Fourier series expansion of this will take this form. It'll be some sort of sum over these scalar values. Okay, not quite scalar value, but excuse me, okay, yes. So here, the vector valued modular form, this is the characteristic function for the coset, excuse me. And each of these will be a scalar valued modular form with a standard Fourier series expansion, or a standard Q expansion, which I write this way for simplicity. But of course, the coefficients in each expansion can be indexed by both the mu and by positive rational numbers. So this pairing here just means you take this linear combination of the scalar functions corresponding to each mu. And that's the pairing that appears in the definition of the regularized theta lift. So the point is you have a way of proving Gros-Sagier and identifying periods more generally in terms of the special values of these functions along CM cycles or along CM points of the spin-Shimura variety, where CM points are really these points that will come from the embedding of an imaginary quadratic field as a zero cycle. Now, let's just say, okay, so let me just write down several theorems. I have 5 minutes, maybe. Thank you, thank you. Okay, I want to say very quickly what's known, and then I want to at least explain how to put it all together to get an interesting perspective on periods, which isn't actually written down in the literature, but it's all there to deduce somehow. So one theorem you have, because you were asking before whether it mattered whether or not the form was holomorphic, it really does matter if it's weakly holomorphic, rather. So Borchard's and Brunier, it's really a theorem of Borchard's, so refined by Brunier, is that if you have, if F is a weakly holomorphic form, and this is key, weakly holomorphic, for instance, that'll be satisfied trivially if it's holomorphic, but you can be a little bit more general than that. With coefficients, with Fourier coefficients for the positive part, because you really only care about the positive part, or the principal part, the holomorphic part, and these will be indexed by the cosets, and m will be a positive rational number. It's typically only going to be supported on integers, and coefficient at 0, given by this. This also plays a role. So if it's cuspidal, if you've got a cuspidal form to start with, everything's a lot simpler. But in general, you can consider more. If you have this situation, and you assume that these Fourier coefficients are rational integers, okay? If you assume that these coefficients for any mu, for any m, are integers, then actually what Borchard's showed is that this regularized theta function, this regularized theta lift, if you evaluate at any sort of point on the complex, any complex point on the Shimura variety, that this will be equal to minus 2 times the logarithm of some meromorphic function whose divisor you can actually compute. So it'll be this thing I call psi, zh, plus another term. Okay, so but it's sweeping under the rug here. So you've got the constant, you've got the constant term. And then there is some sort of complex structure on the Grassmannian which allows you to view z, broadly speaking, as a complex variable, z equals y plus x plus iy. I'm not explaining this, but there's an extra piece which will be determined explicitly by this complex structure. So this y is going to be the real part of the z with this complex structure plus some log 2 pi plus a derivative of gamma 1. If you take f to be cuspidal, you could ignore this, okay? So for simplicity, we may as well assume that f is cuspidal, so that really what we have here is that the value of the automorphic Green's function is minus 2 times the logarithm of some meromorphic function. So for psi fk, a meromorphic function on the Shimura variety with divisor, given explicitly, this is the Borchard's theorem. Divisor of this is given by a linear combination over, you've got over the cosets of the dual lattice, mod the lattice, times the sum over positive integers of the integer Fourier coefficients of the positive part of the harmonic weak mass form, times some special divisors, which can be defined intrinsically in terms of the Shimura variety. Let me just write that very quickly, and then very quickly explain so where the are special divisors of the following type. So these will be given by you'll have some sort of sum over x in a set of this form. So you've got the rational points intersect the level. minus the points that are coming from the points in the vector space that are representing by the quadratic form of these. You've got the characteristic function of mu times the projection of dx. So let me just say quickly what this is. This is the geometry here. So this is the PR is going to be the natural projection to the Shimura variety, and the dx is really just the points in the Grassmannian orthogonal to so this is, excuse me, it'll be the points z in the Grassmannian which are perpendicular to x. Okay, so this is a little bit, the point is you have a very explicit characterization of the values of this regularized theta lift in terms of the logarithms of the values of some meromorphic function whose divisor you can specify very precisely in terms of both the Fourier coefficients of the input form and the geometry of the ambient Shimura variety. So with that, let me say very quickly that, first of all, there's a theorem due to Brunier, a subsequent refinement due to Brunier, which allows you to realize these functions as, I say verbally first what's going on, then write as much as I can. Theorem of Brunier allows you to realize these functions as automorphic Green's functions on the Shimura variety xu with logarithmic singularity along this divisor, which I henceforth call ZFK, okay? And so that means that we have arithmetic divisors in the sense of Erich-Helloff theory available to us. Subsequent theorem of Brunier and Yang allows you to evaluate these Green's functions along CM cycles corresponding to imaginary quadratic fields as some constant coefficient, which is going to be an algebraic number, minus the central derivative value of some Rankin-Selberg function determined by the input, the image of the input form under the differential operator times some Siegel theta series, which in the special case I mentioned will in fact recover the Garasaglia formula, although that's not, it requires several pages to prove that using Shimura lift of F. But subsequent calculations of Brunier-Yang and Andreatta, Goran, Howard, Matapuzzi-Pera allow you to interpret those calculations, those averages of those Green's functions along CM cycles as in terms of arithmetic heights. And then, so let me say as much as I can about this setup in the remaining 3 minutes. Okay, I just try to, I won't go into full detail, but everything I say here is true and can be made more precise. And in a nutshell, all the values of these Green's functions will be periods. Yeah. But it's because of two things. So let me just explain this in a nutshell too. So when, in this situation, where the FK is a weakly holomorphic form, we have this theorem of Borchardt's. Now, a subsequent theorem due to Howard and Matapuzzi-Pera, which appears in Asterix, shows that these are rational. These are defined over Q in some sense, and the values taken by the Borchardt's product must be algebraic numbers, and specifically, they will factor through the ring class extensions of the imaginary quadratic fields over which the points, over the CM points are defined. Okay, so this is so a remarkable consequence of this is that without doing any work at all, you deduce that when F is weakly holomorphic, the values, like thanks to the theorems of Borchardt's plus Howard, Matapuzzi-Pera, the values of the automorphic Green's functions will be, okay, up to this point, it requires a little bit more argument, assume for simplicity this is cuspidal, logarithms of algebraic numbers, okay? And as we saw before, logarithms of algebraic numbers are periods. Okay? So that's a cheap proof right there. We didn't need to do any work. And then the second thing which I want to write on the board is if F is not weakly holomorphic, its image by definition under that anti-linear differential operator is not 0, okay? And in that situation, theorem of Brunier and Yang allows you to compute this value along a CM cycle in terms of some constant coefficients, which will turn out to be an algebraic number, minus the central derivative value of the Rankin-Selberg function of the image of fk under this operator, differential operator psi k, times some Siegel theta series associated to the lattice, which is the complement of the signature 0,2 lattice. And in that situation, so you have that connection, but then you also have this connection, the subsequent calculation in terms of arithmetic heights due to a combination of two works, one by Brunier-Yang, the other by Andreatta et alia, which allows you to think of the evaluation of that Green's function along a CM cycle as being the Archimedean component of the arithmetic height or the Faltings height of the underlying CM divisor along that zero cycle. And then it is, in fact, intrinsic that those values must also be periods. And so what we expect at the end of the day is that all of these are periods as expected by various calculations of the automorphic Green's functions, which these determine along CM cycles, and that there ought to be a description of what is going on in terms of the motivic cohomology of the corresponding Kuga-Satake abelian scheme over the Shimura variety. But let me just say as much as I can. Not so much about the last part, which is still work in progress, but we, like in a nutshell, we believe that there is going to be some, like that exact sequence of spaces of vector-valued modular forms. We believe that there is a corresponding localization sequence for the motivic cohomology of this Kuga-Satake abelian scheme and its fibers, especially the fibers at points in the Grassmannian, which correspond to the CM points, and that somehow accounts for that. And then in terms of this exact sequence in motivic cohomology, we expect that there's a different characterization of this regularized theta lift. In each case on the FK, we believe that when it is coming from a weakly holomorphic form, there will be a motivic class associated to the FK such that the regularized theta lift will be equivalent to some sort of inner product of the regulator of that motivic cohomology class against some 1-1 form, which can be constructed from information about the divisor. And for the FK that are not weakly holomorphic, we expect that there will be a similar construction of the regularized theta lift in terms of some pairing with similarly defined cohomology class against the 1-1 form directly, and that for the last term in the sequence, there will be some sort of way to characterize the regularized theta lift as a pairing composed of the Abel-Jacobi map. And then when we have that connection to the Abel-Jacobi map, the image can be identified thanks to various theorems with some extension class, and we can push out the extension class to get a Kummer extension, and then we can realize these periods that we get as Kummer periods. Okay, but let me just give an outline of what I said the preliminary steps are in deducing. But in a nutshell, these turn out to be automorphic Green's functions for the divisors ZF by a theorem of Brunier. And then, okay, several steps. Let me just write down what we know. But in general, we expect whenever you evaluate those functions at CM points or along CM cycles, you get periods in the sense of Kontsievich-Zagier, and that there ought to be an explanation of what's going on a more abstract level. But on a very analytic level, we can already deduce that we have periods simply from what's in the literature, although it hasn't yet been put together in this way. So people haven't looked at these calculations this way just yet. So here, the theorem, let me be very brief. Everything here has a precise technical description. Theorem of Brunier is that if you're looking at, so you can have f as any harmonic weak mass form. It doesn't necessarily have to be weakly holomorphic. So what Brunier shows is that the regularized theta lift, as I defined it before, this is in fact an automorphic Green's function in the sense of Eric-Halof theory for the divisor ZFK, which I wrote down here. Okay. This is a technical description, so it will extend to a smooth function on the Shimura variety away from the divisor. It will have it'll satisfy some Green's current equation, and it will be an eigenvector for the generalized Laplacian in the Grassmannian variable with a specific eigenvalue, which actually turns out to be n over 4 times the constant coefficient. So that's one important. So this allows us to view. This allows us to view the regularized theta lift as a Green's function, and then we get an arithmetic divisor in the sense of Arakhelov theory. So this means that we have an arithmetic divisor associated to each harmonic weak mass form, which will be given by the information, the divisor itself, together with this Green's function. Okay, so that's what an arithmetic divisor is. And actually, it turns out that the Archimedean part of it, so this has an Archimedean component and a finite component. And it turns out that the Archimedean component can be computed in terms, F is for finite, not for, finite, okay? And it turns out that the Archimedean component will compute the central derivative value of the image, of the Rankin-Selberg function of the image of F under this differential operator times some theta series. And that this will be the constant coefficient that I mentioned. And so there will be a way, okay, let me go very quickly with the deductions. But yes, in a nutshell, the values of these functions at CM points and along CM cycles will always be periods. And let me just say how this works. Okay, so several theorems. So we have theorem of Bernier. Yeah, so I didn't give a characterization of the Green's function, but somehow it satisfies those three properties I said, gives rise to an arithmetic divisor. And so another important theorem here, Bernier-Young. So Invenciones paper from 2008. It's called like Faltings heights of CM points and derivatives of L functions. Is that if you have any signature 0-2 space, which in fact corresponds to some imaginary quadratic field, and you have Z V naught, the corresponding zero cycle, or the CM cycle as it's sometimes called, because it always comes from an imaginary quadratic field, and you let lambda now denote the complement of this signature. Yeah, excuse me, and then like the L naught will simply be the intersection of the maximal lattice, and then so you consider the complement in here. So with this information, you consider that, so if you evaluate the Archimedean component, okay, so if you evaluate the Green's function along the CM cycle, that simply means that you take the sum over all the points in the CM cycle, and you evaluate the function. Then what you get is so this will end up being the finite part of the arithmetic degree. So times the constant coefficient of some. Okay, so of the positive part, or like the principal part, the holomorphic part of the harmonic weak mass form, times the Siegel theta series associated to the complement lattice, times some derivative Eisenstein series. So this is actually going to be there's going to be some Eisenstein series that arises. Okay, so you're going to have some harmonic weak mass form of weight -1 that arises if you. So there's going to be a decomposition of the ambient Siegel theta series for the full lattice. You're going to have the piece that comes from the signature 0-2 space. And you're going to take the sum over the whole CM cycle, and then you're going to use the Siegel-Weil formula to relate that to the special value of some Eisenstein series. And then you use Kuhle's theory of incoherent Eisenstein series to get a relation It's a little bit artificial, but it works, to the derivative the derivative value at 0 of some other Eisenstein series by playing around with level raising operators, or level raising operators. So you've got this constant term, which ends up being the finite part. It's conjecturally and sometimes known to be the finite part of the Archimedean height times the. Okay, so there's going to be some Rankin-Selberg-L function of the image of the harmonic weak mass form under the anti-linear differential operator times the remaining theta series at 0. So 0 for this cell function will be the central point. This will be the derivative. And this will vanish. This will be 0 if f is weakly holomorphic. Then you just have the constant coefficient. But this, in the case where you take the rational quadratic space depth signature 3, 2, to be given by the trace zero matrices of rank 2, rational coefficients, this will essentially be the central derivative L function of like vector valued Shimura lift of the eigenform, which can be related back to the Hasse-Weil L function, remarkably. Okay, so it's a theorem. You can recover Gross-Zagier this way. And so they show, so this is a Brunier and Yang show. Let me just now make, finally, with apologies for the time, is that you have a couple more connections here. So you have here this reproof of Gross-Zagier, which again, I mean, if the F is weakly holomorphic, which is the setting where you can describe the regularized theta lift in terms of the Borcherdt's product, then this is 0, and it's just a constant coefficient. And so you get, you know, yeah. So you have two situations to consider. You have two different calculations, but there are a few more things to consider here. So subsequent works. So one is a combination of Brunier-Yang. This is like the second part of their Invenciones paper, plus paper of Andreatta, Gorin, Howard, and Matapusi-Pera. It computes this in a more arithmetic way and shows that actually if you, this is my notation for the arithmetic height. So if you view the Archimedean component of the arithmetic height, okay, you've got the arithmetic height here. This is the arithmetic height, and you want to evaluate along the CM cycle. Okay, this thing is a CM cycle. Then the Archimedean component of that will be 1/2 of this average that I wrote down before, and this will be precisely this thing. And more generally with, this is more generally if you compute the full height, so not just not just the Archimedean component, what they expect, they conjecture and they often prove. So Brunier-Yang computed for the Archimedean case and conjectured for the non-Archimedean case, and then Andreatta et al. Proved in important special cases for the Archimedean case that this would be given by the degree of the zero cycle divided by 2 times the constant coefficient, which again you can take to be 0 if you like, times the constant coefficient of the Eisenstein series that appears there, plus this central derivative value. Let me write it this way with the complex variable at the front. So you have something like this. And what this means, let me now say verbally. Let me not write any more because I've really gone over time. So we have these automorphic Green's functions which come from regularized theta lifts. And the input datum is really one of these harmonic weak mass forms. So if the harmonic weak mass form is weakly holomorphic, we know by theorem of Borcherdt's that we can evaluate the regularized theta lift as minus 2 times logarithm of this meromorphic function. We know, thanks to a subsequent theorem of Howard and Matepussi-Pera, that the values of the meromorphic function will be algebraic numbers. So in that case, interpreting by the theorem of Brunier, we know that those Green's functions for the weakly holomorphic harmonic weak mass forms will take values in periods. They will be logarithms of algebraic integers. In the setting where that's not true, in the setting where the F is a weakly holomorphic form, which is, it's a harmonic weak mass form which is not weakly holomorphic, you have these calculations, first due to Brunier-Young, which allow you to compute the Archimedean components of the corresponding arithmetic height, and then subsequent calculations of Andreatta, Gorin, Howard, Matepussi-Pera, which allow you to, putting this all together, what you deduce in this case is that the values of the Green's functions along the CM cycles will give you periods as well, because they're going to be the Archimedean components of arithmetic heights along 0 cycles. So it's sort of intrinsic outcome of that calculation. And so in general, what we expect, as I mentioned before, is that there will be some sort of motivic cohomological analog of the exact sequence of vector-valued spaces of vector-valued forms that I wrote down before. And in that sequence, there will be a big diagram. And for the weakly holomorphic forms, there will be an equivalent characterization of the Green's function as some sort of pairing of the regulator of some motivic cohomology class determined by F with some 1-1 form, which is also determined by information about the divisor. And in the more general case where F is not weakly holomorphic, we expect that there's a similar homological characterization given in terms of pairing of a similarly defined class against a 1-1 form. And then the last term, we expect that there's a more general characterization in terms of composition with an Abel-Jacobi map, which allows us to get a connection to extension classes in motivic cohomology, to Kummer extensions and variations of hot structures, and to realize the periods that we get from the special values of the Green's functions as Kummer periods. But this is still work in progress, so I'm reluctant to. Okay, thank you for letting me speak.
Maybe just to be sure.
Yeah.
Everything that you said in the case of everything you said in the case of modular curve,
yes,
it's a special case of this Shimura variety that you took.
Remarkably, yes.
Is done in Zagier, or it is gross Zagier, or there?
This is a good question. Well, let me just say something. What I've said here is apparent to experts after a lot of reading. But for instance, Don Zagier did not. I spoke to him about this last year. Oh. Don Zagier did not know about this proof of Brunier and Young until I told him. It's not well known.
Yeah, but I think Zagier doesn't care about Shimura varieties and so on.
It's true. Not many people know, though. So actually, I've written a 45-page note for my collaborator, partly because colleagues have asked me to explain how it is. So Brunier and Young, if you read their paper, this one, Invenciones 2008, Faulting's heights of CM divisors and derivatives of alpha functions or something like this, they only spell out how to prove the Gross-Zagier formula in a very special case, which I wrote down before. There was a decomposition. So for the Rankin-Selberg alpha function, there's a decomposition into class group alpha functions. And really what they do is they only explain, in a lot of technical detail, what happens for the principal class. But you can modify it and prove the full Gross-Zagier formula using the regularized theta lifts. It's not well known, but I've actually shown, I've spoken to Brunier, of course, and the experts, and of course they think it's obvious. It's not. But you can, from their calculations, although they only give it in a special case, you can in fact derive the full Gross-Zagier for any of the class group twists. So it's an exercise. Okay, it's a 10-page exercise. I've written it in my notes, but it does indeed follow. It's very technical, very perceptive theorem they give, because it's hard to identify the L function. So the L function that they obtain from this calculation will in fact be something like the L function of a vector-valued Shimura lift of the eigenform parametrizing the elliptic curve, and then it turns out to be a proposition to relate it to the Hasse-Weil, L function of U over K. And so it's, if you're interested in how that works, it is section 7.3 in their paper, but I'm happy to explain because I've actually generalized it to prove to myself and my collaborator that it does indeed recover the full Gross-Zagier formula. But it's not well known. It's not well known at all. Even to experts in arithmetic geometry, it's not well known. It's well known to Brunier and his collaborators, but not many others, unfortunately.
Question? So let's keep it for informal questions.
Okay,
Thank you again.
Thanks.